So the next talk is by Xiao Meng. She is a faculty at Zhejiang University in China. During her PhD at CES Saclay, France, she was involved in the efforts for searching the Higgs boson in 4-lepton final state in Atlas experiment. Then she moved to CMS as a postdoc at Johns Hopkins University, where she was involved in measurement of spin and CP-related measurements of Higgs boson in various final states. She is still involved in the same studies like Higgs property measurements these days, including CP violation in Yukawa couplings and EFT interpretations. And it's great to know that she was awarded a CMS Young Researcher Award in 2021 for her work in the Higgs property measurement. So welcome, Xiao, and please go ahead with your talk on CP measurements of the Higgs boson.
Okay, thanks a lot for the nice introduction. You can hear me, right?
Yeah, we can.
Okay, great. And the slides, you can show them in full screen?
Yeah, I can see, and if you can scroll, go to the next slide to see if they're moving.
Is it moving?
Yes. It is.
Okay, great. Thanks a lot. So thanks again for the nice introduction and also for inviting me to give this talk. I'm really very glad to give you an introduction to the CP measurement of the Higgs boson. So let's start with the very basics. So what is a CP symmetry? CP stands for the charge and parity symmetry. It basically describes how physics laws perform under charge flip and spatial mirroring. So this is a nice cartoon that I copied from a CERN web page. This is also from some news measuring the Higgs CP probability. So you can see that basically it tells you how the Higgs performs under this spatial mirroring, whether or not it changes its behavior. So in principle, when we write down the law of physics, there's no rules telling us whether or not our nature should follow the CP symmetry. So this is where experimental measurements come into place. And it plays a very important role in the history, telling us what is the property of the CP symmetry in various interactions. So in the early days, people think it's natural that everything CP and also T symmetry, until when the first experiment tells us that in weak interaction, both C and P symmetry is violated separately. But then when you combine the two, then CP is preserved. And later on, also people find some rare processes where the CP in combination also is violated, for example, in the kaon decay and some other processes found in the HCB experiment, that they found that CP does not really conserve. So what about the STAN model? What does it say about CP? So in the STAN model, there's also room for CP violation, and it exists in the quark mixing matrix, yes. But the size of it is really, really small. So does it mean that in nature we should not expect any CP violation? The answer is no. Actually, the CP violation is really vital to the matter-antimatter imbalance. So we live in a world which is composed of matter, and we do not really see antimatter, and this is the imbalance that I'm talking about, and this really bothers physicists, because in the very early universe, they should be equally created. So why do we only see matter nowadays, not antimatter? And theorists say that CP violation is the key to explain this imbalance. That means we should really look for the CP violation and see what gives our nature the picture that we see now. So where do we start to look for CP violation? Before the Higgs boson, there were a lot of efforts looking for CP violation, but none of them are significant enough. So Higgs boson is the last component in the standard model. It's a completely new particle that gives us very new ways to look for CP violation. And but what about its prediction in the STEM model? And what does it say about the Higgs? So in the STEM model, not only the Higgs conserves the CP symmetry, but it's also the only scalar in the STEM model, meaning that under CP operator, it's a CP even particle, meaning nothing changes its behavior. But is the STEM model prediction true? This we don't know. We have to examine it in experiments. So in 2012, right after the Higgs boson was discovered, there is this Higgs hunting workshop just 2 weeks after the discovery. And in that workshop, theorists give their point of view on whether or not the Higgs boson is the STEM model CP even scalar. So Peskin says that given that the Higgs decay to WW and ZZ at the rate close to the STEM model, he guess, or he's quite certain that this is the CP even spin zero state from the standard model. Strassler, on the other hand, is a bit more open, saying that it's most probably that this is the STEM model Higgs boson, but it could also be a mixture of CP even and odd states. So when we have a mixture of CP even and CP odd state, that means the CP symmetry is broken. Now, 10 years later, we of course know that both of them are right. We have not seen any CP violation signs from the Higgs sector. But just coming back to the time when they make these guesses, do they really could get the CP information of the Higgs just from the information they get at that time? So what do we have at that time? We have 2 nice peaks of the Higgs boson in the Higgs 2 4 lepton final state and Higgs 2 gamma gamma final state. Both are very nice and clean peaks. And these are the mass peaks that helps us to identify the Higgs cell. But do the mass peaks carry CP information? The answer is no. So if you have a CP odd state, it would also have this nice mass peak. It's just, you have to look further into this Higgs boson. So how exactly do we know what is the CP of the Higgs boson when it interacts with particles? We have to look further. So since the Higgs boson was found first in the bosonic final state, meaning gamma gamma, WW, and ZZ, so it's natural that we start to study the Higgs boson CP property in these final state, meaning study its interaction with vector bosons. And you can write its interaction in a very general way, which describe all the Higgs interaction with all vector bosons. And you can also write this nice sketch where Higgs boson decays to 2 vector bosons, and if the 2 vector bosons further decay to 2 particles, that means the 4-body final state, then you can have this construct these nice planes of decay and try to construct angles that describe the correlations between all the final particles. So there are in total 5 angles in this plot. And if you do look at the distribution of these angles, you do see that when this Higgs CP is CP even or CP odd, which is red and blue, or when there's a mixture of the 2 with different phases, say a positive phase in green and a negative phase in magenta, you do see that these angles show very different behaviors, also shown in this figure. That means if you have a Higgs boson decay to 2 vector bosons and further decay to 4-body final state, then you can easily identify its CP property. But there's also one thing to remember. If you look at the right plot, which shows the cosine theta is a plane of the Higgs decays to 2 vector bosons plane. So if you only have a 2-body final state, meaning the Higgs decay to 2 vector bosons, but do not further decay, then this angle, which is the only angle in this plane, does not carry any CP information. of course, here I'm talking about spin zero hypothesis. When the Higgs boson has other spins, it's another story. So if it's a spin zero and the two vector bosons do not further decay, you cannot really tell whether it's a CP even or CP odd. So this applies to the Higgs gamma-gamma final state because the two gammas do not further decay. And there we cannot really tell if the Higgs is a spin zero, whether it's a spin, whether it's a CP even or CP odd. You cannot tell from this angle. So we can only do this analysis in ZZ or WW final states where these two particles further decay. And this is indeed what experimentalists do. So we do see that these angles carry enough information and there are a lot of them, but experimentalists do not want to deal with multidimensional problems. They like to have an elegant and simple observable which helps them to tell what is the property of the Higgs boson. And this is the usual techniques they use in the end, meaning integrate a multidimensional information into one single observable. And here they use matrix element-based methods, meaning you have all the final state particle kinematic information. You give them to the matrix element calculation, and then you build an observable based on this calculation that is smart enough to tell apart the CP even and CP odd. And that's indeed the case. If you look at here, the Higgs 2ZZ24 lepton plot, the dashed and the solid lines stand for CP even and CP odd state, and these observables are smart enough to tell apart the two hypotheses. And they also design similar observables that is sensitive to the mixture phase. So you see that if you have no mixture, then this observable is completely symmetric. But if you have a mixture with positive phase, then you have a forward-backward asymmetry. And vice versa, if you have a negative mixture, it actually will go the other way. So using these techniques, people can use very simple observables to measure the Higgs boson CP information. In addition to the matrix element methods, there are also machine learning techniques, which are widely used later in all kinds of CP measurements. So using these things, one can measure the Higgs boson CP, but before that, one should ask, what is the spin of the Higgs boson? Is it spin 0, 1, or 2? Because under these different spins, you can always have different CP properties. So people first use the techniques that I described before to identify the spin of the Higgs boson. And you can see that the spin 1 and spin 2 are widely excluded. And the observables they use are exactly described as matrix element-based method to separate spin 0 and spin 2 hypothesis, for example, shown in this plot. So this tells us that most probably the Higgs boson is a spin 0 state. So here, then you just need to focus on spin 0. And if you write down the scattering amplitude of the Higgs boson couples to two vector bosons under spin 0 hypothesis, then you do not have a lot of possibilities. You have three kinds of terms. The first term is a stem model-like spin 0 scalar term. The odd term. So since we here are talking about CP measurement, I focus on the CP even, stem model, and the CP odd terms. So in practice, we just need to know what is the size or what is the contribution from these two terms. And you see that there are coupling constants modifying these interaction patterns. A1, which modifies the CP even term, and the A3 modifies the CP odd term. And eventually, when you present your result, you could present in whichever way you like. And CMS and Atlas chose very different ways. The CMS to which section fraction of the CP terms. And the Atlas gives the coupling constant ratios, which is the A3 over A1. So if you think about it, these two ways could be translated to each other. One single line of formula, and then the two results could be translated. So coming to the result, so by the end of round one, both Atlas and CMS could measure the CP mixture of the Higgs boson when it decays to ZZ and demonstrating the CP odd fraction or contribution to less than 40%. So this is, of course, a very good news. Because you see that the best fit value, which is centered at 0, also this one is close to 0, meaning the nature thinks the Higgs is more or less like a STEM model, a Higgs boson with the CP even state with 0 contribution from CP odd actually. So is that the end of the story? Is this precision good enough? And we ask ourselves. So here I show a table coming from the SNOMED 2013 report. So this is right after the Higgs boson, where people gather together and think what should be the target of the LHC and the high lumiere LHC. How precise should we measure all kinds of Higgs properties? And this table summarizes the wanted precision for Higgs CP measurement. And the target here is set up when you think there is a 10% mixture of the CP odd state. This number comes from the combining all the constraints from experimental measurement and also very plausible theory predictions that is compatible with the STEM model, yet gives room for CP violation to explain the matter-antimatter imbalance. Target 10% mixture of CP odd. And how does that translate to our measurement? So for Higgs BB coupling, that translates to 10 to the minus 5 cross-section contribution from CP odd. This is extremely small. And this is because in Higgs BB couplings, the CP odd terms are coming from higher order terms, and its cross-section is very much suppressed. So if you have a 10% mixture from the CP odd, it only contributes to 10 to the minus 5 cross-section of the total. That means if you want to use Higgs BB coupling, on the other hand, if you look at the Higgs fermion couplings, you see because in the Higgs fermion couplings, both CP odd and CP even terms are coming at the same order. It seems that using the fermion couplings is a better way to probe the Higgs CP. But that's not the end of the story. Actually, if you look further or into details of this,
I think there is some glitch. Yeah. Internet, yeah. The voice is breaking at times.
Okay, sorry, can you hear me now?
Yeah, you can go back to the previous slide, that will be nice.
Yeah, so you were not hearing this?
Yeah, there was some, delay, or rather we missed some parts of the statements that you made. Hello, Shyam, are you there?
I think now they are. You see the participant, please. Oh, he is still connected. She is still connected.
Now she's one of us. Maybe she will come.
Yeah, okay.
Okay, I'm very sorry that I got disconnected. Can you hear me now?
Yeah, we can hear you now, Shyam. Please share your slides.
Yeah, sorry about that. So I will continue with my slides. Did you lose me at this slide?
Right, we wanted you to start from this slide. Yes.
Okay. All right. Sorry about that. So I was talking about this table basically. So we want to set up a target. How precise should we measure the CP odd mixtures? And we set up the target at 10% mixture from the CP odd state because it's based on the experimental observations at that time and also plausible theoretical predictions that is compatible with the current measurement, but also gives explanation of the matter-antimatter imbalance. But 10% mixture of the CP odd state means the CP odd cross-section in Higgs VV couplings is down to 10 to the minus 5. This is because when you talk about Higgs VV couplings, the CP odd contribution is at higher order than the standard model. That means this cross-section is extremely small. So even if you have a 10% mixture, it contributes only to 10 to the minus 5 of the cross-section. On the other hand, if you look at Higgs fermion couplings, then because CP odd and CP even are at the same order, the cross-sections are also at the same order. So you only need 10 to the minus 2% precision on the cross-section measurement. So it seems it's impossible to constrain the Higgs VV couplings at a scale of 10 to the minus 5. But then if you look further into this table, you see that the two middle column tells you the expected sensitivity from the LHC at 300 and 3000 inverse femtobus. And these two rows seem to give a quite very stringent constraint. Where do they come from? There are also Higgs VV couplings, but comes from VH and VBF production modes, while the first one is doing the Higgs to ZZ decay. So what is the difference between the production and the decay? If you look at the vertices, they are all the same. It's a Higgs coupling to two vector bosons. But for VBF and VH, these vertices have higher Q squared. And what does higher Q squared give you? If you look at this plot, this is also coming from the Fino study, that as you increase the Q square of the interaction, then the standard model or the CP even interaction has a downward cross-section prediction, while for the CP odd term, you have an increasing cross-section. And that means at higher Q square, your cross-section from CP odd over CP even is boosted a lot. So if you are searching for CP violation or CP mixture, you should go to higher Q square because there you have a more visible BSM contribution. And this is what VH and VBF does. This gives you a higher Q square vertices. So you could naively expect that it can give you better sensitivity. And when people start to use these informations in experiments, they indeed get a very enhanced sensitivity. If you compare the left and right plot, the left plot is coming from round one using only Higgs to ZZ and WW final state decay. And the round two result, just to have more data, but most importantly, they explore the VBF and VH information. And there you gain a lot. You see that the constraint on the CP odd cross-section contribution go down to 5 multiplied to 10 to the minus 4. So that's quite close to what kind of the precision we needed to be sensitive to 10% CP odd mixture. So this is indeed a very impressive progress. But people would think, oh, why don't you use that in round one? In principle, you also have VBF and VH in round one data.
Ming?
But in round one, if
Hello? Previous slide.
Hi.
What are the numbers in this bracket?
Sorry?
What are the numbers in the bracket?
The numbers in the bracket, those are expected. So one number is expected and the other one is observed.
Thank you.
Okay, thanks. All right, so let me move on. So we were saying, why don't we do it in round one? Because if you look at the data plot in round one, we have under the mass peak, we have around 20 Higgs bosons. And as we know that gluon fusion is a dominant production mode, you would not have so many VBF events. So analyzing them will be very difficult. When it comes to round two, you have a lot more data, and here under the peak, you have around 200 Higgs. This make it easier to analyze VBF events and BH events separately. And indeed, this is what people do. So people categorize the events under the mass peak into, say, gluon fusion categories, VBF categories, and also VH categories. And in these clean categories, where you can study the VBF events exclusively, you see a much larger enhancement from the BSM, meaning CP odd contributions. And this is where you gain the most of the sensitivities. So this could be done in the Higgs 2 lepton final state and also in other final state, because when you start to talk about VBF production, then the Higgs could, in principle, decay to whatever it wants to, and the production information is still there. So this gives you the benefit that you could really combine all the Higgs decay final state together and get a very good sensitivity. So CMS did this analysis where Higgs decay to tau and 4 lepton combined together. And in tau analysis, they also try to design categories sensitive to VBF and GGH separately, and you can see their categorization here. And in each category, they design observables that are sensitive to CP odd and CP even, which is shown in each block here. The blue and the red ones are the CP even and CP odd hypotheses, and you do see that they differ a lot in each dimension. So by doing this, the tau plus ZZ could give you an even more stringent constraint on the CP odd contribution, which is up to 10 to the minus 5. Also, the bracket gives you the expected result. And in this case, it's because the data gives a very upper fluctuation, so it constrains much better than expected. Okay, so this is one way to get a better sensitivity to go to higher Q-square. So in addition to the production mode, what other ways to get higher Q-square? The offshore region. So in this event, I've already heard a lot, so I will try to not be them. The Higgs boson decays to ZZ, it could go also offshore because the mass is smaller than the 2Z mass. So in the offshore, in the standard model, there are about 10% events. But then if you have CP odd contribution, which is shown in the green line, you see that it gets very boosted. So by studying just the offshore events, you could constrain the CP odd contribution very well. And this is what CMS did. So by combining the Higgs ZZ decay to 202 nu and 4 lepton, this is a 202 nu offshore events. The red ones are the Higgs offshore tails, and all the other ones are from the background. By using these events, one can constrain the CP odd contributions up to 10 to the minus 3. So this is also a remarkable.
What is the horizontal axis?
Improvement in the, yeah.
What is the horizontal axis? Mass of the lepton, dilepton? No. What is it? In the middle plot?
May? Can you hear?
Sorry?
No, I wanted to know in the middle plot what is the exact horizontal axis? Is the angle
The left plot?
no, the middle plot, the color
Middle plot.
Yeah.
This is a 202 new offshore region. The transverse PT or mass, I don't remember which one is it.
fine. Yeah, I wanted to know what is the variable. Okay, fine.
Yeah, sorry, I think I covered the axis. I would check it and come back to you. But it's definitely the offshore region where the because you have the two neutrinos, so you cannot really construct the invariant mass of the two Z's. So it's probably transverse mass or PT of the system.
Yeah, okay, fine.
Right.
Okay.
Okay. Okay, so this is about the Higgs VV couplings. And as I mentioned before, doing these analyses are quite difficult because the contribution from CP are at the next level. So they have quite small contribution in cross-section. But if you focus on the Higgs fermion couplings, then CP odd and CP even contribute at the same order or same level. So you could really probe into the two equivalently. And there has been a lot of studies on Higgs fermion CP studies. And if you look at the numbers of the publication, you see that they are very new. This is because the fermion couplings are kind of harder to see. So many of the processes or final state were observed very recently, like the TDH final state production mode. It was only observed maybe around 2017. So analyzing the CP property has to wait a little bit. And this is why they come very recently. And here you see that on the fermion CP measurement, we have quite a lot of them. We have the gluon fusion ones, the Higgs 2 tau tau, and also the TDH. So let me go through them a little bit. The very first Higgs fermion CP measurement were done on TDH production because top is the heaviest fermion that couples to the Higgs, and because of its heaviness, the CP violation in this channel is also the most obvious. So TDH also gives you a very good signature to probe the CP. If you focus on the TDH production, you could have multiple planes that probe the CP nature of the Higgs, the TDH production plane, the TD bar decay plane, and the top decay plane. So in total, you could construct way more angles and invariant mass than, say, Higgs ZZ couplings, because there are a lot of planes here. And indeed, if you look at the angles in each plane, they also bring very abundant information about the CP, say, CP, this angle tells you the CP odd and CP even look very differently. The mixture also look different from them, and this TD bar decay plane could tell the sign of the mixture from each other. So this is great news. That means TDH really could give you sensitive CP information. But one should also remember that this is a very complicated final state. It has a lot of final state particles, which are very difficult to get reconstructed all at once. So from in most of the cases, you cannot get the full information of the full decay chain. And that makes the analysis using matrix element analysis very difficult, because for matrix element analysis, you need to know the full information of the final products. So when people really do the analysis, they start to use machine learning techniques to separate different CP information. And the first analysis to do this is a gamma-gamma final state, where TDH Higgs decay to gamma-gamma. And people train the machine learning techniques to separate different CP hypotheses and then put events into different categories. For example, if you look at this category, the standard model, which is a red one, has a higher number than the CP odd, which is a blue one. And in this category, it's the opposite. The blue one, which is CP odd, has a higher number than the CP even. So by putting events into different categories, you could be sensitive to the CP nature of the Higgs. And then people just fit the invariant mass of the photon two photons all together in all the categories to determine what is the CP of the Higgs. So the right plot is what you get if you extract the information from the simultaneous fit and then put the fitted number of signal into each bin. Bin means the categories. So you do see that, for example, for category 1, 2, 3, the CP odd events are looking at the blue one are different from the red one, which is the CP even events. And the fit from the data tells you that the data point follow the CP even hypothesis. So this way, you constrain the CP odd contribution to be less than probably 40%. And Atlas also perform more or less the same studies. And these are the categories they designed. There are a lot of them, 20 categories, each designed to be sensitive to different components and CP components. And then this plot shows a fraction of events from different mixtures of the TDH, THQ, and THW. So Atlas also gave a similar result on the constraint of the CP even and CP odd coupling constants. So both CMS and Atlas exclude the pure odd hypothesis at around 3 sigma. So the fermion Higgs Yukawa coupling also do not have a pure odd hypothesis, and their mixture cross-section fraction is right now less to be constrained to be less than 45% around. So this is a good start. And then people further investigate more production modes or more vertices, that is a gluon fusion. So we all know that the gluon fusion comes dominantly from the top loop. And this is why people use it to constrain the Higgs TT Yukawa coupling. But one also need to remember that if there are no accompanying jets in this production, then you cannot be sensitive to the CP. You have to use the additional jets to carry the CP information of the Higgs. This is why this analysis was only done in round 2, not round 1, because you need to have gluon fusion plus 2 jets. And this topology is actually very similar to the VBF topology, where Higgs is also produced in association with 2 jets. So this is a very similar kinematic phase space as VBF, and one has to separate the VBF from the gluon fusion plus 2 jets. So analysis have to design observables that are sensitive to these 2 different phase spaces. Then if you look at the delta phi of the 2 associated quarks or gluons, you see that they show very different pattern when it's a CP even or CP odd, or when you have a mixture with positive or negative sign. So this is very good news. One can use this very simple observable to probe the CP of the Higgs boson in gluon fusion. And this is what Atlas did in Higgs 2WW final state by just looking at the delta phi JJ. They could constrain the CP of the Higgs gluon vertex. And this is their experimental measurement. And in the end, you see that their sensitivity is not that good because there are not so many gluon fusion plus 2 jet events. This is a low cross-section topology. And here they make an assumption that they don't know what's happening inside the gluon fusion loop. So they treat this vertex as effective Higgs glu vertex, but still they could be sensitive to the CP of it, whether it's a CP even or CP odd. Of course, one has the option to also interpret it as a top Yukawa coupling. And this is what CMS did using Higgs to 4 lepton and Higgs to tau final state. So one good thing about this delta phi JJ or gluon fusion plus 2 jet is that you can see that it's really sensitive to the mixture of the CP. So whether it's a positive or negative mixture, you have very different behaviors. And in CMS, people design machine learning or matrix element-based techniques to be sensitive to only the sign of the mixture. So you see that this observable and this one. When you have no mixture, it's straight flat. But if you have, let's say, a positive mixture, then it's forward-backward symmetry. And you can imagine if you have a negative mixture, then this will flip to the other side. So it's a tau-tau analysis. So this really could give you a hint when you have some mixture of CP or CP violation. And in the tau-tau analysis, as I mentioned earlier, you have to separate BBF from gluon fusion because the kinematics are quite similar and they carry different information. So in the end, the tau-tau plus 4-lepton constrain the CP of the Higgs gluon fusion vertex as this one. So the CP odds fraction is constrained to be less than 9% in the negative side and 90% on the positive side. So here it's a little bit symmetric. This is because the variable that is sensitive to the sign of the mixture shows some kind of a preference. Of course, the SNAP model is still very inconsistent with the observation. So as I said, you can also interpret the gluon fusion vertex as a top Yukawa coupling. And here you gain extra information because if you think the gluon fusion is completely coming from the top Yukawa coupling, then under a CP odd hypothesis, its cross-section should be 2.38 times the SNAP model, while for TDH, it should be 1/3.56 cross-section of the SNAP model. So these two have a dramatic difference. And if you combine the gluon fusion and TDH, then you could really constrain the CPR contribution very well because the two goes the opposite direction. And this is what CMS 4-lepton analysis did. They design categories that are sensitive to gluon fusion plus 2JET and also TDH. And they measure the top Yukawa coupling CP from these categories, and they could really give a very stringent constraint on these kappa T and kappa T tilde, which is CP odd and CP even coupling constants. And let me come to the last CP analysis, which is the Higgs tau-tau. So Higgs tau-tau is another Yukawa coupling that we have, and people are also interested in whether there is a CP violation in this interaction. And indeed, similar to the planes that we introduced in previously Higgs VB, the Higgs decaying to tau, where tau also further decays to other particles. These planes give you information about the Higgs CP that interact with the taus. And indeed, if you look at the angles between the two decay planes, it shows you that when you have CP even, odd, or mixtures, these angles look quite different. So analysis just to use this variable to extract the CP information of the Higgs. And here they consider a lot of tau decay final state. Here I just show the row final state where you do see that CP even and odd have very different behaviors. And in the end, they combine the quite 4 different tau decay final state to constrain the Higgs CP. And if you look at the phi CP, which is the angle between the two decay planes, you see that the data agrees with the CP even, which is a red one, quite good, well. So they also give constraint on the CP odd and CP even coupling constant in this plane. So they also exclude the pure CP odd hypothesis at 3 sigma. This is all very consistent with all the current findings that the Higgs couplings to either vector boson or fermions show a CP even nature with very limited CP mixture or CP violation inside. Okay, so I now come to my summary. So it's now 10 years after the discovery of the Higgs boson, and we have seen impressive progress in the CP measurement of the Higgs boson. It starts with the Higgs vector boson couplings, where people can put some constraint on the CP odd contributions. And later on, people just develop more advanced techniques to look at BBF, VH, and offshore regions where you have boosted sensitivity through the higher Q squared. And this allows people also to combine multiple final states to get a better sensitivity. Then recently, there are a lot of studies on the Higgs fermion CP measurement, and this is completely a new domain. And we have seen that people measure the Higgs top, we call it coupling through TDH, TH, and gluon fusion, and the Higgs tau tau through its decay. And as you can see that for the fermion CP measurement, the precision is not that good compared to the target one. So there's still a long way to go, and people will come up with more advanced techniques, just like Higgs vector boson couplings. And we do really look forward to these improvements in the future. So that's it. Thanks.
Thank you, Sean, for the excellent talk. We already have Soumya with a question. Soumya, you can go ahead. And
Yeah,
others-
can you hear me?
Yes, I can hear you.
Okay, so in your Miller distribution, like D0, D background for the Higgs to ZZ or Higgs to WW, these variables are mostly taking the kinematic features of the leptons, right?
Yes.
So if we are doing the same analysis, or if we are trying to reconstruct these variables for the Higgs to gamma gamma, but where we have only the two gamma, I mean, in the final state and the kinematic properties of that, can we also introduce the jet, I mean, the two jet property plus the two photon properties inside this Mela to get these variables? Is it the correct technique, or we have to rely on only the four kinematic properties of the four objects decaying from the Higgs?
I think you could try, but in principle, if you are talking about, say, gluon fusion plus two jets, then the Higgs could decay to whatever. It doesn't really care.
No, we are actually focusing the final state with the Higgs two photons.
Yeah, I know. So for example, if you look at this diagram where Higgs could decay to photon or whatever,
yes,
then what's important in this diagram is the two additional jets and the initial state quarks or jets. So if the Higgs decay to two photons or to taus or to z's, it will give you the same separation, because here what's important is not the two products from the Higgs, but these four legs.
Okay, and
so,
another,
yeah, you can do that in gamma final state. That's not
another thing in this slide, in the plot, whatever we are seeing, that there is a difference of the delta phi JJ variable for the various hypotheses, but we have checked that these are mostly for the higher MJJ values or higher eta region for the two jets. I mean, mostly these phase space is also overlap with the VBF as well, because in the lower values of the MJJ, if we check that the distribution of this plot, I mean, on the left hand side plot in this slide, so if you check that the distributions among themselves are not enough, the different, so we have to go to the higher values of MJJ, and that phase space is also occupied by the VBF portion as well. So is the addition of the GGH on the VBF gives any extra information?
Yes, actually, that's a good question. So indeed, if you want to get the sensitivity in gluon fusion, you have to go to very high MJJ, which is very close to the VBF topology. But here, it depends on which Higgs CP properties you're measuring, because for gluon fusion, in principle, it is the Higgs GG coupling or the Higgs TT coupling that you are looking at. And for VBF, you're looking at Higgs VV coupling or Higgs ZZ or Higgs WW coupling. So these are, in principle, two very different couplings. You could, of course, assume that these two should have the same behavior, meaning if you are a CP odd, then you should be CP odd in Higgs VV and CP odd in Higgs GLU or CP odd in Higgs TT. You could do this assumption, but in principle, they should be two separate parameters. And indeed, in this region, if you assume that if it's a CP odd, it should be CP odd in all different couplings, then you get extra power separating CP even and CP odd. But when we do analysis like this, we don't do this assumption.
Meng, could you repeat the last one?
I'm just saying, if you assume that what dominates VBF, which is the Higgs VV coupling, and what dominates the gluon fusion, which is actually Higgs fermion couplings, have the same CP nature, meaning if they are CP odd, they're CP odd everywhere. Then of course, when you do gluon fusion analysis, you have extra constraint from the VBF events, because VBF also have different behaviors in this region. But when we do our analysis, say, do this assumption, so we assume that the VBF could be whatever it is, it's floated in our fit. It could be CP odd or CP even or mixture. We don't really use this information to constrain Higgs gluon fusion CP.
Okay, thanks.
Thank you, Arun.
Hey, thanks for the nice presentation. So I was wondering if there are any discussions how to combine the CP results from different, say like from different production modes and as well as from the decay. So for example, in the Higgs to tau, we have both production and decay, but how do we really combine them if it is possible, and if there are any discussions about it?
Yeah, so currently the combination is done per analysis site. So there's no central organization on the huge CP combination. But what you ask is a good question, because when you have production and decay, which relates to two very different couplings, then you have to be very careful when you do the combination. You could assume that when it's CP odd in Higgs VV and Higgs fermion, but this assumption is not necessarily true, and it doesn't have to be true. So so one has to be very careful when you do this combination. Usually when we do combination, we focus on one kind of coupling. Say, if I want to do Higgs VV coupling, of course, I can combine VBF, VH, Higgs decay to ZZ, and also Higgs decay to tau, but we don't put extra information of the Higgs tau decay CP information. There, we just allow it to be whatever it is. I think this is a more natural, independent way to do the combination.
Yeah, thanks. But it should be possible to combine, say, from the TTH and the Higgs to tau.
Actually, also because TDH concerns Higgs TT coupling and tau is Higgs tau coupling, it doesn't have to be the same mixture. Just like when you do signal strength measurement, you of course can assume Higgs fermion couplings all follows the mass proportional scaling, but it doesn't have to be the case.
So you are assuming that the fermion couplings, each one can be different.
Yeah, in principle, they're independent. It doesn't have to follow what the STEM model predicts.
Meng, I have one more question. Just this plot on the left. So there are two discriminators. Is that true? One is so which one is the first one? This D0 versus D0 means positive versus CP odd versus CP even, that discriminator, and then you do this signal versus background, this DNN.
Exactly. So the DNN is what separates the signal from background. And you can see that from left to right, you have less background.
Yeah.
You have more signal. And then D0 minus separates it even from odd.
The point is, unless, this is what my confusion is, unless there are enough number of particles or handles to make the discriminator. So tau may be okay, and for TTH, we are we better off compared to tau H?
You're talking about TDH decade to tau? And you're wondering if there are enough events to
about couplings, means when we are okay, fine, okay, because for tau,
I suppose
have some missing energy. and to what will be the input variables for the neural network versus the problem with Higgs 2 gamma gamma, because there you don't have many handles.
Yeah. So for example, in Higgs gamma gamma TDH analysis, we don't really have a lot of events as you see in each category. And we extract the number through this fit. So, but in principle, you can use very limited number of beams to perform a very good analysis. And here in principle, you see that D0 minus only have 3 beams, and you could do a quite good analysis already.
Yeah, okay. We'll look into the slides carefully.
Mm-hmm.
Are there any further questions for Sean? Comments? Okay. If not, let me thank Sean for the nice talk.
Nice talk.
Great. Thanks.
Okay, so let's move